All right, homework 4. So first we're going to explain the advantages of the Broyden, Sherman, Morrison method over Newton's method, derive Broyden update formula and its form when used in conjunction with the Sherman-Morrison, explain the geometric idea behind the Lagrange multipliers, and then implement the Broyden's method with the Lagrange multipliers and a slack variable to find the local minima of a 2D Rosenbrock function constrained by the region y is greater than or equal to, y is greater than 2x minus 1. So, first question, explain the advantages of the Broyden, Sherman, Morrison method over the Newton's method. So, most notably, that's the computational power associated with Newton's method is much greater than the Broyden, Sherman, Morrison method. This is mainly due to the fact that the Broyden, Sherman, Morrison method only requires an initial Jacobian as well as an initial inverse to be evaluated, whereas every iteration after that it can use a previous Jacobian or previous inverse in order to solve the equation, whereas Newton's method you have to constantly calculate the Jacobian and the inverse with each iteration, as well as the fact that Newton's method has a dimensional limitation. The Broyden, Sherman, Morrison can solve for n dimensions, whereas the Newton's method is pretty much locked to a one-dimensional analysis. And then also the Newton's method is prone to some round-off errors, whereas the Broyden, Sherman, Morrison method is not. So we're going to go into actually deriving the Broyden update when putting it into the Sherman-Morrison method. So start by deriving the Broyden formula. So look at some initial ideas. So our function at any given moment is just going to be our function evaluated at an x sub n or a previous x value, x sub n minus 1. And then our functional difference is going to be our delta f. So pretty much what Broyden did is he looked at two equations. Our first one is this f sub n minus 1 plus our Jacobian, previous Jacobian, multiplied by our delta x or our previous or current x minus our previous x, and then hoped for a value of 0, right, to try to solve for the equation. But in reality, what ends up happening is you're going to have a linear approximation that doesn't always get you to a 0 value. So in order to account for that, the next Jacobian will be used as opposed to the previous Jacobian in order to find the f sub n value that you would get. And then comparing those two equations, you're going to subtract them in order to get a delta j, which is your change in Jacobian from current to previous, and your delta x, and then set that equal to an f sub n. And then the second equation that you looked at was looking at your Jacobian matrix multiplied by a chosen vector, and then setting it equal to a previous Jacobian of the same vector, assuming that the chosen vector is perpendicular to your change in x. With this assumption, you can say that your vector multiplication between your chosen and delta x value is going to be equal to 0. In addition, this equation works because we can assume that the chosen vector does not vary because it's of an unknown direction. So our previous and current Jacobian multiplied by the same chosen vector will have the same change. Therefore, they're equal. So if you take the difference between those Jacobians and multiply by the vector, you're going to have the same as this initial equation here, and then set it equal to 0. So pretty much what Broyden did is, after examining these two equations, what he wanted to do was find a value for delta j that you could substitute in to satisfy both equations. So this j sub n minus j sub n minus 1 would be equal to something that satisfies equation 1 on the top here and equation 2 on the bottom here. So looking at equation 1, what we want to do is we want to try to find a fraction where we have our fn on the top and then something on the bottom and top in order to cancel out this delta x. So in order to do that, and then subbing it in for this delta j. So in order to do that, we're going to start by setting a f of n on the top of our substitution variable, I guess. And then what we're going to want to do is we're going to try to get rid of this delta x by multiplying by a delta x transverse. And this delta x transverse, when you multiply it by your delta x, what you're going to do is you're going to essentially get a constant matrices, so a 1 by 1 matrices. And if you divide that 1 by 1 matrices by itself, you'll essentially cancel them out. So you'll be left with an f sub n to be equal to an f sub n. So this initial equation can be satisfied when implementing this substitution in. So what we also need to check for is the fact that this variable will work with our second equation. So in our second equation, when we plug this into our delta j, we'll be left with a delta xn transverse multiplied by our y vector. And since we know that our y vector times our delta x is 0, we can say that our y times our delta x transverse is also going to be 0. Therefore, when we multiply them together, we'll be left with an f of n times 0 divided by delta x transverse times delta x, which will be equal to 0. So 0 equals 0. Great, we have a second equation also satisfied, so we can say now that our substitution variable for our difference in Jacobians will essentially be this guy right here. So after we get this guy, we can rearrange him as Broyden did. And if we go down, we can kind of see it a little bit better in this picture for whatever reason. We'll have our Broyden, and then we'll also look at evaluating our Sherman Morrison, which allows us to get an inverse of a given function using the previous inverse. So pretty much what we're going to do here is we're going to notice the similarities between our Sherman Morrison and our Broyden method. So in our Sherman Morrison, we can see that this a plus UVT, all inverse, is going to be equal to this equation. So we notice here that at our Broyden method, our a is more or less our previous Jacobian, our u is pretty much this fraction here, and then our v is this delta xn. And then if we take the inverse of that whole thing, we'll end up with this Sherman-Morrison simplification here. So kind of integrating that in here, you can see Broyden plus Sherman is going to be essentially substituting all of our a's for j's, keeping our u and v's the same, and just specifying the fact that our u is again equal to that fraction, and our v is equal to that delta xn. And after plugging that in and kind of getting this mess of a fraction, you can simplify it a little bit by noticing that we have our magnitude of our delta x on the denominator of each part of our fraction. After you, again, evaluate this with a common denominator. So you'll take away those delta x magnitudes. And then you'll also notice that our delta xt times our delta xn is going to cancel out with our magnitude here, because it's essentially the same thing after subtracting. And then you'll be left with our Broyden-Sherman-Morrison method equation right here, which we'll now code into Python so that we can have a working form. So I went ahead and already imported our JAX-NumPy as JMP, as well as configured JAX in order to be a 64-bit version as opposed to the default 32. Essentially all this is going to do is it's going to increase our accuracy with a slight sacrifice to speed of computing power. But let's go ahead and create our function. So we're going to define a Broyden, if I can type, Broyden Sherman Morrison. This was from a previous attempt, I guess. And we're going to want to have the user input a function, input an x vector. We're going to have them import a Jacobian if they choose. If not, we'll set it equal to none, and we'll create an if statement to automatically calculate the Jacobian based on JAX-NumPy, or I guess JAX Jacobian later, if they don't specify. Then we'll also create a tolerance to see how close we really want to get our iterations towards our zero value. And then we're going to set max iterations to be equal to 500, which we'll use later when we're in the Rosenbrock function. We're going to set an x max equal to a Jack's numpy infinite positive, and then an x min equal to a negative Jack's numpy infinite. And we'll go ahead and start defining our function. So first what we want to do is we want to create a Jacobian of our function. If our j is none, so if the user doesn't input anything, but if they do input something that isn't none, we'll just leave the Jacobian as whatever the user specifies and assume that they're right. So going on the assumption that they don't input anything, we're going to have Jack's Jacobian manually look at the inputted function and turn it into a Jacobian. And then next, we're going to have our Jacobian set equal to our JF of evaluated through our x vector. So this essentially covers our basis whether or not the user inputs a Jacobian or not, and then evaluates whatever they input as well. And then we're going to take our initial Jacobian inverse, which is the only time we'll have to do this unless we have a weird alpha value, which we'll get into later. So then we'll go into linear algebra of our inverse of our j function. And then we'll also evaluate our inputted function given the inputted vector x. So that essentially gets us all of our initialized variables that we'll then use in order to get our equation satisfied. So what we're going to start out by doing is creating a giant for loop. So for I in the range of our max iterations, which in this case will be 500, unless the user specifies another number, we're going to use our Newton's method to determine whether or not our dx is, or what it even is initially. So we'll do a matrix multiplication of our negative Jacobian inverse multiplied by our function. And then what we're going to want to do is we're going to want to find our alpha. And our alpha is more or less going to be a semi-arbitrary multiplication factor that we're going to use on our dx term. So essentially what it's going to allow for is if we ever overstep how far we're changing our dx, we'll have a correction factor alpha that will ensure that that overstep doesn't go over our x max or below our x min, which can be specified by the user given whatever function they're working with. And this alpha will essentially allow us to take fractional steps in order to avoid getting some sort of error where we're not going to get any convergence. So first, what we're going to want to do is we're going to want to look at our alpha max limits. And what we're going to want to do is we're going to want to look for the location at which our x plus dx is going to be greater than our x max, and where that happens, we want to have our x max minus our x min divided by our dx, which is essentially going to be evaluating our alpha, right? And assuming that that does not have at all, like if we don't have an x plus dx that goes over that maximum value, we're just going to assume we didn't overstep our dx, and we're just going to set that alpha equal to 1, aka we'll just take that full step instead of a fractional step. And then we want to make sure that that alpha value, we're going to essentially find the maximum alpha value at which you still stay within the limits, but we want to also make sure that we're finding the minimum of that maximum alpha value so that we don't get an error later in our function. So we're going to do a Jackson numpy min of our solution, and then we're going to essentially copy and paste this for our min limit, but in this case we're going to be looking at obviously our x min and making sure our x plus dx, and in this case dx would most likely be negative, when that value is lower than our x min. So whenever that happens, we're going to again evaluate for our alpha and then set it equal to 1 if we don't need to. And then we're finally going to actually get an alpha. So between the x max and x min, there's going to have to be an alpha min between the two that will satisfy both. So we will have, again, a minimum of our alpha max, and then our alpha min. And within this alpha, we're going to want to create a while loop. And what this while loop is going to do is we're going to check to make sure that our alpha stays above a arbitrary 0.01 value. Essentially what this is doing is making sure that our alpha doesn't get so small that we're not really changing anything, as well as if we have too small of an alpha, we could be overshooting where we're actually supposed to be, which we'll get into later. But while that is above the minimum alpha value, we're going to essentially test out whether or not our dx is okay. So we're going to set a dx try equal to our alpha fractional jump multiplied by our dx. And then what we want to do is we want to create a new x vector, at which we take our current x's and then we multiply it by our change in x that we're trying out. And then we want to be able to evaluate how those new x's impact our inputted function. After doing that, what we're going to do is we're going to find our jmp.linear algebra of our normalized distance or line from our new function. So again, seeing how far away from the origin that this new function is, and then subtracting it by more or less the same thing, the distance from the origin of our previous function. So this is essentially going to be our delta norm, or change in norm, I guess, whatever. Change in distance from that origin. And what essentially we're going to be checking for is if our d norm is getting bigger, if we're falling further away from where we want to be, like closer to that origin point, we're going to say that we need to multiply our alpha by a half step again. So it's going to just be even more reduced than where it was. But assuming our norm actually is getting closer to our 0 point, we're just going to break our while loop, right? And then once we get out of our while loop, we're going to again check for if that alpha value does indeed get too small. We're going to want to reevaluate our Jacobian because it could just not be working out at the current state that it's in. So we'll do linear algebra dot inverse of our Jacobian function evaluated at our x's. And then if this is the case, we still want to continue through our iterations. We don't want to break out, so we'll just go ahead and continue because we're still in this giant for loop, right? And now, after that, we're going to want to essentially reset all of our new variables onto our old variables so that when we go back through the for loop, they'll be considered old. So we're going to say our dx is going to be equal to our dx try. We're going to say our f is equal to our fp, and our x is equal to our xp. So after we have our chosen, or our new functions overridden essentially, what we want to do is we want to check for when we actually converge on our 0 point based on our given tolerance, right? So if our absolute value of our function is less than our tolerance, so we've accepted or we've met our criteria essentially, we want to also check for all of these too. We're just going to want to break out of our for loop. And this is essentially going to be where we start to go into actually calculating our Broyden, Sherman, Morrison method. So we're going to use the same variable names as they use for the Sherman Morrison method, so our UV. So our U, we're going to have to reshape and essentially dimensionally expand using our Jackson-Umpy expand dimensions. And then we're going to look at our FP, which is our new values, right? And then V, do pretty much the same thing. Expand dimensions of our XP. No, of our DX, because we're now changing. We're not looking at just the XP. And then we're essentially now going to plug in what we have here. So this equation 3 is what I have it specified as here. By solving for our Jacobian inverse, this is going to be equal to our previous Jacobian inverse minus our previous Jacobian inverse, matrix multiplied by U, matrix multiplied by V transverse, or transposed, and then previous Jacobian inverse, and dot inverse, I didn't do that before, did I? Cool. Divided by the quantity of our 1 plus our V transposed, and then matrix multiplied by our J inverse, matrix multiplied by our, oh wait, no, we already did V. So U, and that will be our Broyden, Sherman, Morrison method evaluated completely. And from this function, what we want to do is we want to be able to return our X and our F values. And then we'll go ahead and run that. Error, invalid syntax. That would help. So make sure you got your colon. Invalid syntax, again, make sure you got your colon. Return outside of function. There we go. Did I accidentally? That's fine. Okay. So now we'll go into question 3. So explain the geometric idea behind the Lagrange multipliers. So you can see you have a constraint function given as a g sub, or g x sub y, g x y equals 0. And then we have an f function, x x y. Each one has some contour lines. G is given in red, f is given in blue. Within these contour lines, there's a gradient that can be given for each x and each g, right? each contour line is essentially showing the fact that f, at least in the blue, is either increasing as you move up towards this middle circle, or it's decreasing, kind of going into a little pit. And you can assume the max or minimum or maximum is somewhere in this middle point here. It could change based on where the contour lines are drawn, but you'd assume it's around here. And then G kind of looks like it's moving either to the right or to the left. As it moves to the left to right, it could be increasing or it could be decreasing. But at any given point, you can kind of see that there is a perpendicular line that you can draw at each given point. So at G, at this point, you can see it's moving up and to the right. And then at F, at that same point, it's kind of moving down, right? So as you move down, F is increasing or decreasing. And as you move up and to the right, G is increasing or decreasing. But as you kind of move along this line, you can draw lines for your F and your G function. And eventually, as you move down towards this middle section here, the lines will get more and more to the right for G and more directly to the left for F. And at this point here, you can see that the gradient for G and the gradient for F are collinear, so that you can see that delta G, or gradient G, sorry, moving to the right at the same sort of rate and same direction as your gradient F moving to the left. Given this, you can say that if you added a Lagrange multiplier onto your constraint function, which is your gradient G, if you multiply that on to that gradient, or sorry, that G constraint function, what would end up happening is you would end up moving along that gradient F. So you would stay within that F gradient function. In addition, you could also add a constraint function that isn't inequality. You can actually do like an inequality. So at this point it's 0, but maybe you can say anything that's greater than 0, or in the case that we'll be examining, y is greater than 2x minus 1. So you can say maybe this, we want to look at f values and constraint values that satisfy this entire right side of G. So anything that's greater than 0 or less than 0, it kind of just depends on what you're looking at. And then essentially what we want to do now is we want to use this Lagrange multiplier in order to find the minimum point within a 2D Rosenbrock function, which is given by this equation down here, and find that minimum that fits within the region of y is greater than 2x minus 1. So now what we want to do is we want to actually get into question 4, so implementing it. So first we're going to start off by defining our first function, which is going to be our Rosenbrock. Our Rosenbrock function is going to take in an x value, and we're going to want to return essentially what's printed up there. So return 100 times the quantity squared of our x sub 1, since we have an xi plus 1 there, minus our x sub 0, which is our x sub I, and that x sub I is squared. Squared. And then after that, we're going to add our 1 minus x sub 0, or x0, which is again just the position, and it looks like that entire quantity is squared. And then we're going to want to get into our constraint function. So we'll define constraint to be equal to x, or to have an input of x. And what we're going to do is we're going to want to return essentially our y is greater than or equal to 2x minus 1. So what we're going to do is we're going to take our x0 squared plus our x sub 1 plus our x sub 2, which is going to be our slack variable that we're going to add essentially to ensure that we stay on that positive side of 2x minus 1, or the greater than 2x minus 1. So our slack variable is going to be x sub 2. We're going to square it to ensure that it always stays positive. And we're adding it in order to assure us that we are on the high side of y. So it's greater than y, or y is greater than 2x minus 1. And then we'll just subtract 1. And I don't think I hit that. There we go. And then finally what we want to do is we want to define our Lagrange when the user inputs x, or in this case it will be the Broyden method. So our Lagrange is going to be essentially our Rosenbrock at our x minus our lambda, or Lagrange multiplier, which is also an adjustable, tunable variable that essentially we're using to slide across our given plane in order to find the minimum in this region. So we'll take that and then multiply it by our constraint function, so it allows us to shift, right? So our constraint evaluated at x. And this is the same as just saying L is equal to F minus lambda G. And now we're going to actually get into defining the function. So what we want to do is we want to get our d of our Lagrange, so essentially our gradient, right? So we'll get our Jax dot gradient of our Lagrange, and then we'll take some initial guesses for our x vector. So we'll create an array, and we'll get guesses of 0.1, 0.1 for the positioning. For the, I believe it is, this one's the slack variable, so we'll just say like 10. And then for the Lagrange, we'll say 0.1 again. And then we'll get our Broyden Sherman Morrison method. We will import our gradient function, import our initial guesses, and then we will print out whatever our x's are. So position, slack variable, Lagrange multiplier. And then we'll print out our f in order to assure us that our f is converging to a 0 point or close to it based on our tolerance. And then we'll get our Rosenbrock function evaluated at our x positioning, in which case it will take in x sub 0 and x sub 1. It will not take in x sub 2 and x sub 3 since it's not specified. So no worries there. And we'll go ahead and run and hope. And we should get the same values as printed up here when I have tried to do this in a previous iteration. It'll take a little while as it moves through all the calculations and all the iterations. Hopefully we're not stuck in a loop. Are we stuck in a loop? So we've defined all of our functions. Did we run this? We ran it. JF. So we've taken the inverse on the max iteration, define that. J inverse, dx try. Okay, wow, that took a long time. But you can see here that we have our position x0, x1. We have our slack variable. We have our Lagrange. And then our f function we have printed here. We're all at like e to the negative 12th, which is about what we'd expect. It's about 0, so we're good here. And then we can see that our actual minimum value of our Rosenbrock function, given the constraints, is going to be our 0.08567. And that is it.